as it's an online seminar, can everyone who's not talking mute their microphones during the talk? And I will try to remember to do the same myself. So today we've got Eva Maria Müller from Oxford, who's an expert in cosmological data analysis. And so Eva did her PhD at Cornell and then went on to do postdoctoral research at the ICG in Portsmouth before moving now to Oxford on a research fellowship. So today she's going to be telling us about the latest and final results from the EBOS survey. So Eva, whenever you're ready, take it away.
All right. Well, first of all, thanks for having me. And I'm going to give you an overview over SDSS, in particular the cosmological program of SDSS, so the Sloan survey, focusing on the latest EBOS results. But of course, we are a collaboration with hundreds of people. So this will be partially also not just my work, which was on the cosmology paper, but on behalf of the whole collaboration. Yeah. So as the name says, the extended Baryon acoustic the Baryon oscillation spectroscopic survey is the extended version of the BOSS, in particular extended in terms of redshift coverage and going to higher redshift. As I said, it's part of the Sloan digital sky survey using data from the Apache Point Observatory in New Mexico. So SDSS, the redshift service and the cosmological redshift service have been going on for over 20 years now. And with EBOS, this concludes the entire cosmology program of SDSS. So there's still manga and other things going on for SDSS, but it's more galaxy evolution, other things. The cosmology part is done now. So it started with nearby galaxies that are in green. And then for BOSS, we have the LRG sample, the luminous red galaxies, so the old galaxies. We also have a sample now in EBOS for the ELGs, the emission line galaxies, which you can see in blue. And on top of that, we are using data from the Lyman alpha forest, as well as looking at using the clustering of quasars. So that you can see in yellow, it's covering all the higher redshift, so covering redshift from 0.8 to 2.2 and even higher. So the BOSS survey and the EBOS survey is a spectroscopic survey. And just to give an idea on how this data was being taken for those that haven't seen it before. So what the BOSS survey and also EBOS survey used were these aluminum plates where there were holes drilled for each of the targets and the objects that we wanted to observe. And then actually all the fibers to get the spectrum for this individual object had to be plucked by hand. Now, there are thousands of these aluminum plates out there. So whenever you see maybe an outreach talk, it's very nice to hand these out just to get you an idea of actually the complexity that goes into obtaining this data. So now here you can see the sky coverage for the different samples that we had in BOSS. With the BOSS LIG being the largest sample, with all sky coverage in the NGC and in the SGC, but overall the LIGs are the biggest samples. The ELG, we were a bit disappointed. We were aiming for more, but there were problems. So we ended up with much less sky coverage than we wanted. The original plan was also to have both the quasars and the ELGs roughly covering the same area as were the BOSS LIGs. But that's what we have. So now within this 20 years of BOSS, it was really, or SDSS and the Redshift service of SDSS, it was really a journey of firsts. So here on the left, you can see the first detection of any BAO signal. So the Baryon acoustic oscillation in the distribution of galaxies. So this was in 2005, where you can see the BAO basically give you this bump in the correlation function of your galaxy pairs. So that's really what we're trying to measure here. On the right-hand side, you can also see in parallel, there were a group analyzing 2DF, which roughly came out at the same time, studying the BAO in Fourier space, so studying the power spectrum. And again, following a similar analysis. So SDSS had the first BAO signal in galaxies. And here you can nicely see, this is from a BOSS result, where you can see how the BAO can work as a standard ruler in bins in different redshifts. Now, it was not only the first BAO detection, but it was also the first BAO detection within the Lyman alpha forest. So using the forest of the Lyman alpha lines in the spectrum, you can also do a similar analysis looking at the 2-point statistics. So again, here, correlation function as a function of separation between your points. And again, you can see there was the Busk et al. In 2013, so the first BAO detection in the Lyman alpha forest. The aim for eBOSS was really, so this is state of the art, you could say, before eBOSS, where you can see we had this high redshift Lyman alpha point, so redshift above 2. We had the LRGs, these are the BOSS points. And also from SDSS, the main galaxy surveys, and 6DF. Now, with eBOSS, we really were trying to bridging the gap here with the quasar sample. So again, SDSS and eBOSS had the first BAO detection using quasars as tracers, and now filling the gap within the redshift range between 1 and 2. So this was from 2018, the Atta et al. Paper, and on the left, it's from the targeting paper, where you can see the galaxy distribution. Now, we were not always the firsts for emission line galaxy. WiGLES were before us. However, where we are not first, we are at least largest. So it is the largest sample of emission line galaxies, having over 170,000 ELGs, covering a medium redshift range from 0.6 to over 1. Now, the ELGs are fairly important in the senses that ELGs will be the main tracer for the DESI instrument, the dark energy spectroscopic instrument, which used to be called the Big BOSS. Basically, is an extended version of BOSS, but covering roughly 14,000 square degrees. So eBOSS here with the ELGs was a bit of a test run for DESI. All right, so this is now the number densities, so the redshift distribution of the main samples that for the galaxy and quasar that were analyzed in eBOSS. And you can see here we had a different targeting strategies, if you will. So the quasar sample really is fairly low number densities, but covering a really wide redshift range from 0.8 to 2.2 and even a bit higher. We have the LRGs mainly at lower redshifts, where you can see this is CMAS, so this is BOSS, and now eBOSS extended further into higher redshift, covering the range up to a redshift of 1. And then we have the ELGs, really high number densities covering this intermediate range. So now just going a little bit more into detail, what are these Baryon acoustic oscillations? Most of you for sure know this, but just as a reminder, we are using this Baryon acoustic oscillation scale just as a standard ruler, in the same way we use supernova as standard candles. So in supernova, where we know intrinsically the luminosity, or at least we can calibrate it, and then by measuring that, we can trace the history of our universe, we can do the same thing with the BAO scale. Or in other words, we can look at where is that bump in the correlation function. And then as a function of redshift, that gives us information about the expansion of our universe. Now, what we're really measuring here with the 2-point statistics is we're measuring the over or under densities of galaxy pairs. And we can do this along the line of sight and perpendicular to the line of sight. Now, along the line of sight, we get a delta C, where you can see here it depends on the expansion rate of our universe, h of c. And the angle, so the angle between the galaxy pairs is related to the angular diameter distance. However, it's also important to note that we have this little factor of RD in here, the sound horizon, and it's going to become more important later on. So I will talk more details about what exactly RD is. All right, so here is just an example for the BAO measurement in our LRG EBOS sample. You can see the data and the model fit to it. So what I wanted to point out is, I think you might have seen on the archive that there were over 20 papers, I think, out. So one of the reasons is we have all these different tracers, and for each of the tracers, they were basically two groups doing the analysis. One group always looking in configuration space. So as a function of your correlation function as a function of distance, or in Fourier space, looking at the power spectrum. So if you want to know any more of the technical details of how exactly this measurement was being done, then I would refer you to these papers, each one for one of the different tracers, because each of the different tracers have a bit of a different systematic treatments and a few other tweakings in the pipeline. So now this is the main summary of our results, or indeed all the cosmological results of SDSS. So what is plotted here is the BAO distance ladder. So these are all our different measurements as a function of redshifts. And what we've plotted here is the BAO measurement with respect to what you would expect for the best fit Planck 2018 lambda CDM measurement. So here, this line 1 just means that you get the same dA and H as Planck. So now here you can see our different tracers. The SDSS MGS is the main galaxy sample at very low redshifts. We have the 2 BOSS bins from the previous analysis. We have the 3rd new bin for the LRGs, so for these old luminous red galaxies, pushing to higher redshifts. We have the emission line galaxies, the young galaxies, the quasars, and also the BAO from the Ivan alpha forests. And as you can see, we have really good agreement with the best fit Planck, with 1 point slightly above below, but nothing you would not expect just from statistics. No, but the BAO is not the only thing you can do with galaxy clustering redshift surveys. We also have something called the Redshift-space distortions. There, the basic idea is that the galaxies have a peculiar motion. And because of this velocity, your true distribution is kind of squeezed. So you can see here, you have the galaxies infalling into the overdensities. So this will appear to be closer to us than it actually is, and this will appear further away overall, giving this distortion effect in the distribution of the galaxies. Now, this is important because with the RSD, the redshift-space distortions, we can directly measure the growth rate of structure in our universe. And with that, we can test general relativity. So in GR, you would roughly expect the growth rate to go omega matter to 0.55. However, most modified gravity theories predict somewhat of a different growth rate. So by testing the growth rate, we can test general relativity. Now here's an example for the measurements, again, for the LRGs, where you can see is without the RSD, you would just get something spherical, and now you get this squeezed effect here. Right, so now same plot as before, but this time with the redshift-space distortions. Or even more specific, what we are measuring is F times sigma 8. And again, we're plotting this here relative to what you would expect to the Planck predictions. Again, the main galaxy sample, the BOSS LRGs, eBOSS LRGs, ELGs, and the quasars. For Lyman alpha forest, RSD is, well, let's say very tricky. So we don't have an RSD measurement from the Lyman alpha, only from the quasars and the galaxies. But then again, we find really good agreement with the predictions of Planck lambda CDM. All right, but now that we have this measurements of dm, dh over d and f sigma 8, what can we actually learn about our fundamental cosmological models with that? What can we learn about the acceleration of the universe or curvature or neutrino mass? So this is a very famous plot where you can see you've plotted here the matter densities on the x-axis and the dark energy on the y-axis. So this is from the supernova cosmology project almost 10 years ago, where you can see for the BAO was very degenerate. So with the BAO by itself, you could not tell if there's dark energy or not. Zero was within the 1 sigma. Now, this is specifically a model where you allow the curvature to vary. Now, keep in mind, if you just consider the basic Friedmann equation, with a flat universe, omega matter equals 1 minus omega lambda. So this is exactly this line here that gives you a flat universe. This is how it looks now, 10 years later. Again, what plotted here is on the x-axis matter. Here you have dark energy, and in blue is what you get now from Baryon acoustic oscillations, combining the full SDSS sample with the galaxy quasars and Lyman alpha. And you can see now that we are with BAO, without any other probe, you can get a detection of dark energy. So if I just flip back and forth between those two, you can see how much the improvement here is. And the reason for that is really because we're now, in the past, this was basically just one BAO measurement and one redshift. And now here we are tracing anything from 0.1 to up to 3.5 for the Lyman alpha. In particular, including the Lyman alpha and the galaxy BAO really allows you to break degeneracies that give you this really good constraint on dark energy. Now you can also see the improvement in the other probes. So here supernova really is the Pantheon sample, and CMB TNP means the Planck temperature and polarization. So this is in gray. All right, But then we thought, what about dark energy? And now here in particular, this is one of the most general models that you could assume as far as the background evolution goes. So here we have 3 additional parameters compared to lambda CDM. So we're allowing the curvature to be free. That's what this O means. And we are parameterizing the dark energy equation of state, which is W, with 2 extra parameter. Now, a W of -1 means a cosmological constant, and WA of 0 as well. What you can see here now, what is interesting, you can see in blue when you add in Planck together with BAO, with our SDSS measurement, you can see that we're really, really good at constraining curvature. Here, this omega k is the curvature of our universe. Not so good when it comes to the evolution of dark energy, at least in this general model, because of degeneracies. On the other hand, you can look at Planck plus supernova. We're really good at constraining W0 WA, but not so good on the curvature. So here, it's a good example if you really want to constrain these more general models, that you need to combine all the different cosmological probes, the CMB, the supernova, and the BAO. On top of that, you can also see is how we really recovering a lambda CDM, with W0 being -1, WA being 0, and the curvature of our universe also being 0. So overall, we find very good agreement with the vanilla standard lambda CDM model. So a model with a cosmological constant. All right, you might say, wait a minute, you say everything is great in agreement with the other probes, but what about the Hubble tension? So you might have heard before that there is a discrepancy, what H0 value you get from local late time measurements. So for example, the holy cow or the shoes measurements. So that is the Rees et al. Measurement of H0, where you use a distance ladder approach using supernova data to get your value of H0, which is roughly around 74. On the other hand, the constraint or the value of H0 you get from Planck, from CMB, seems to be more around 68. So now there is a 4.4 sigma tension between these local type H0 measurements and early type CMB measurements. The question is now, what can we learn from BAO specifically about the H0 tension? So now this is kind of our summary plot. And because it's very busy, I'm gonna just walk through step by step, kind of explaining the different contours that you can see here. So now this here, this gray bands, these are the local H0 measurements from Rees et al., the shoes distance ladder approach, around 74. Now remember earlier when I talked about what we're measuring is angles on the sky and differences in redshifts that are related to the Hubble parameter and the angular diameter distance, but not exactly. What we do have here is what we're actually measuring is the H over RD and the M over RD. What that means is, while we're very good at constraining the overall matter density of our universe, with BAO by itself, it's hard to tell what H0 we would expect because of this degeneracy. So here you can see RD inversely proportional to H0. So what we need is additional information on this RD. So RD is the sound horizon, so the distance traveled by sound waves between the end of inflation and the decoupling of the baryons from the photons after recombination. Now, in particular, what goes into the formula is we need additional information on the baryon density of our universe. So here what goes into is omega BH squared and omega MH squared. So the matter density and the baryon density. However, we do have additional constraints on the baryon density that is mainly CMB free, which is from the Big Bang nuclear synthesis. So the BBN constraints gives us information on the baryon density. And if we include this information on the baryon density, you can see how this degeneracy between the south horizon and H naught is being broken. And you can also see is that what you get from the combination of all our BAO measurements and the BBN, a very low H naught value compared to the local distance ladder approach. Now, keep in mind that this low value is in good agreement with Planck. So we have an alternative way on constraining H naught that agrees with Planck, but disagrees with the distance ladder approach. What we were then trying to do is a so-called inverse distance ladder approach. So inverse distance, so basically going from high redshift to low redshift to fit the H naught value at redshift of 0. A ladder because we're using combination of CMB, then the BAO intermediate redshifts, and then the supernova at low redshift to really calibrate this ladder. And again, we're using this very general model with the open or free curvature and W0 WA CDM to have as little constraints as far as the model that we are assuming here when we're doing this approach. Now keep in mind that while this parameterization of W0 WA might not 100% cover each and every dark energy model that is out there, it is pretty good in covering the vast majority of models. So what we are trying to do here is kind of assuming a model without making any assumptions about dark energy, or at least late time dark energy. And what we're getting here is those contours in magenta. So now this is a combination of CMB, BAO, and supernova, making no assumptions or almost no assumptions about the background evolution. And you can still see that we cannot reconcile this low CMB H naught value with what you get from the distance ladder measurements. So that really means that dark energy can't really explain this discrepancy or explain this tension between the local distance ladder measurement of H naught and Planck, or also now BAO and BBN. Oops. But of course, you can also think of it the other way around. So what you can see here in purple is now we used our measurements of the BAO, and instead of breaking this degeneracy by getting constraints on the baryon density, we went the other way around. We got constraints on H naught. So we used this local distance ladder measurements and then to see what RD we're getting. So the idea behind that is people keep talking about an H naught tension, but it could equally be interpreted as an RD tension, so a tension in the sound horizon. So now, which kind of leaves us with mainly two options on how to solve this tension, at least in my mind. So one obvious solution is that there's just some systematics in the distance ladder approach that we don't know yet about, or that there is something about the very early universe physics that goes into the CMB constraint on the sound horizon, that there is something additionally happen there that we don't understand. But as I said earlier, it's very unlikely that there's any kind of dark energy causing that. All right, so now the reason, again, why we're getting this really good H0 measurements compared to before. Here you can see the BAO measurements split up in low redshifts and in high redshifts. So the low redshifts are the boss galaxies, and the high redshifts are the quasars and the Lyman alpha BAO. We're assuming the same prior on the baryon density, including the BBN. And what you can see nicely here, there is different degeneracy between your parameters, between the low redshift and the high redshifts. And combining all of these different BAO measurements at different redshifts leaves you with a very nice tight constraint of H0, which is roughly H0 plus minus 1. All right, so that was talking about the H0 tension, so the expansion at redshift of 0. But there's also a second tension, or I would say a discrepancy, that has been talked a lot about within the cosmology community at the moment. So in particular, it is sometimes called S8 or also sigma 8 omega matter tension or discrepancy. So sigma 8 is the amplitude of linear matter fluctuations on a co-moving scale of 8 megaparsec. Basically, it's scaling your power spectrum or correlation function up and down. And what you can see here, again, in blue, you have the Planck results. And then the other colors and dashed dotted lines are different lensing measurements. So DES, the dark energy survey. So this is a weak lensing survey. And you can also, in red is the Planck lensing, so the lensing of the CMB. And you can see it's not as severe as the H0 tension because there is a bit of overlap, but on average, all of the lensing experiments want a bit lower omega M, sigma 8 degeneracy direction than the CMB. So the question is now, what can we with the galaxy clustering and with our redshift surveys learn about this discrepancy? Now, we are, with RSD, with the Redshift-space distortions, what we are measuring exactly is F times sigma 8. So the growth rate times this amplitude factor. And we were a bit disappointed because, as you can see, our results are in agreement with all the other surveys because our constraints are fairly large at this point. But it also highlights the future of these RSD measurements soon with DESI, also with the Euclid survey. We will be able to get tighter constraints on the sigma 8 value to have more of a say when it comes to the discrepancy. So it is an alternative way, again, to get constraints on sigma 8 that is not from lensing. Now here is just an overview if we combine the different traces of the different surveys. So Planck now means all of Planck, so Planck temperature polarization and lensing. SDSS means both the BAO and the RSD. And the DES is the so-called 3x2. So it is the weak lensing and also the clustering analysis that they have. And here the bands is the omega matter value that you would get from the supernova from the Pantheon sample. And you can see again, SDSS very diplomatically agrees with both the Planck and the DES, having a bit of a higher sigma 8 than what you would get with Planck. But in the end, the 1 sigma overlap between the blue and the gray and the blue and the red. And also we're very nicely recovering the same meta constraints as the supernova. Now the supernova can't constrain sigma 8, so that's why it's only banned here. All right, so the last topic that I wanted to talk about is our constraints on massive neutrinos. So here in the slides, you can see a lot of different things. So let me just again walk you through it. So with cosmology, we can only constrain the sum of the neutrino masses. So we know from particle physics that we know the differences in mass between the 3 neutrino species, but not the absolute individual masses. So what that means is from particle physics, we get 2 different so-called hierarchies. And that means is normal hierarchies where you have 2 neutrino species that are almost massless and 1 with a higher mass. So this then gives you a lower limit on the sum of the neutrino masses of roughly 60 MeV. Or this differences in neutrino mass also allows you the opposite. So have 1 neutrino species that's basically massless and then 2 that have a higher mass, which then gives you a lower limit on the sum of the neutrino mass of roughly 100 MeV. Now here you can see our constraints in combination with Planck and also supernova on the sum of the neutrino masses. So in red is only Planck, CMB, and lensing. Sorry, the CMB lensing. Then in green, if we include the BAO measurements, in red, the RSD. And here you can nicely see the contribution from the RSD really improves our constraints a lot. And then also if we combine all of these different probes. Now, our 2 sigma constraints are exactly at the edge of this 100 MeV, meaning that we're kind of at the cusp of ruling out this inverted hierarchy. However, you can also see in dashed, this is actually the Gaussian fits to our MCMC analysis. And you can see that a lot of our parameter space in this unphysical region, which means this interpretation of what these 2 sigma actually mean becomes more tricky. So that at this point, we cannot for sure rule out inverted hierarchy. But the inverted hierarchy is getting less and less likely. And we're getting there. So this is also a prospect for Euclid and DESI. We're more expecting some neutrino masses around 30 or 40. So at that point, we should be able to differentiate between these different neutrino mass hierarchies. All right, so this is kind of a summary as far as cosmological model goes within the last 20 years. So stage 2, what it means is it includes WMAP, so CMB survey before Planck. For the BAO measurements, it's DR7, so the first BAO measurement that you could see, and it's one of the first plots that I've shown you, and the JLA sample. Now here we assumed fairly general model with 3 extra parameters. So free curvature of our universe, the sum of the neutrino masses, and also letting the dark energy equation of state vary. So this is roughly where we were 20 years ago. And orange, then you can say, is what you get if you just use WMAP, JLA, and our SDSS BAO data. And it's interesting to note, for example, is that we don't really need Planck to end up with a flat universe. So this is really just WMAP and BAO gives you a pretty tight constraint on the curvature of our universe, and it is in agreement with zero. Now, stage 3 is now, this includes DES, so the Dark Energy Survey. It includes Planck for CMB and a Pantheon sample for supernova. And you can see also we're getting even tighter constraints on the curvature, neutrino mass, and dark energy. But everything is confirming the standard lambda CDM model. So a cosmological constant with W in agreement with -1. All right. So this was a kind of a quick overview of some of the results that we had with SDSS and with EBOS. So it concludes the stage 3 dark energy surveys with spectroscopy. So there is more coming up on the lensing side with DES, but as far as spectroscopic redshift goes, that's it. So the next stage 4 is quickly coming up with DESI and Euclid. BOSS and EBOS, we have over 4 million spectra. So it's one of the biggest, or the biggest spectroscopic sample with the largest redshift range than any other probe, probing everything from redshift of 0 up to 3.5 with the Lyman alpha forests. We achieved percent level and precision on the BAO distance scale at each of these different redshifts, and also have growth measurements, so RSD measurements up redshift of 1.5 with the quasars. So, and I think that's where I'm gonna end and take some questions.
Okay, thank you very much, Eva. It's really, really good. I'll clap on behalf of everyone because I think it's hard doing it remotely, but that was really interesting. Thank you. I'm sure there'll be many questions. Acoustic, I can see your hands up.
Yeah, sorry, there was also something going on in the chat, but I couldn't multitask.
Hi, Eva, can you hear me?
Yes.
Hi, Eva, thanks a lot for your talk. I was just wondering, I'm sure there's a lot more exciting science coming out from this data. So can you tell us maybe a couple of new papers or analysis that we should be expecting in the next, I don't know, 6 months or a year with this data, and maybe combinations with other data or other science cases that you're studying?
Are you talking about your paper?
No, not at all. Not at all. I'm talking about maybe voids, FNL, stuff like that.
Yeah. So here I'm mainly focused on the BAO and RSD, but it is true that there are a lot of other things you can do as well. There are 2 analyses on voids, and I think one is already out. So using the voids as in the distribution of galaxies, again, to constrain DM and DH. There is a measurement on inflation, so FNL, this non-Gaussianity parameter, which is something, it's one of my projects as well. It has been delayed because it's very tricky studying the systematics or so, but I think we're getting there, so I'm hoping that this is out within the next weeks to maybe 2-3 months. There are the cross-correlation studies going on, so I think, I don't know if you want to say more, so I'm working with Acoustic on cross-correlating the LRG and ELG sample with the H1 intensity mapping from the...
No, but I was really asking for the, I don't want to advertise this, but thanks. I was really asking for the, for the really high impact stuff. So for example, a specific question I had was, these neutrino results seem really amazing to me. So do you think that maybe the voids, combining the joint analysis with voids, can pin this down even further, or the theory modeling is not ready for that yet?
I have not seen it, I must say. So I'm not sure if anybody specifically is working on it. I mean, the voids is a bit tricky because the way they're doing is kind of, they need to apply this reconstruction in every step of their MCMC analysis. So to that extent, it's a bit tuned, and I'm not sure how robustly. I think there would be more studies needed before you can do that robustly for neutrino masses.
Okay, thanks a lot.
Hi, a couple of questions here from Will Sutherland, if I can. Yeah, going back a while, when you had those various pretty colored two-dimensional RSD pictures. That was sort of back towards the beginning, or about a third of the way through, I think. They seem to have a kind of dip in the middle. What is actually plotted there? Is this R squared psi or something, or that
is F sigma 8.
No, I mean in those 2D plots with it's psi. It's a correlation function, right? That's that's on the color scale. What is on the color scale?
You mean this?
That thing, yeah. Yeah. Okay, yes, it is. Okay, I didn't catch that when you went past. Yeah, it is S squared. There's an S squared in there. Okay, so that explains why that looks kind of, because I remember we had a plot of 20 years ago. We had one of those, for the first one of those from 2DF, and this one we didn't have the S squared in our plot, so it looks kind of different. The second question I had was about the quasars, the BAOs at redshift 2.2 or 2.3 or whatever. There used to be a kind of 2.5 sigma or something anomaly on that. They were okay. So that's kind of still. Is that still there, or it's gone? That's going away now. Is it the?
So you mean this Lyman alpha forest
yes,
point?
The forest part of the forest. So the forest point has basically moved closer to lambda CDM. Yeah.
Yeah. So it's actually interesting because they did not change their pipeline at all. So it's really just they added in more data. So going from the previous data release to this, the shift is really caused by the data, and what it was previously, it was a bit over 2 sigma, and it's just, that.
So it was just purely statistics.
It was purely statistics. Yeah.
Yeah. Right. Interesting. Thank you.
Ava, I have a question about the neutrinos. Could you go back to the neutrino? Yeah, I didn't fully understand this, because why are the peaks of the probabilities at negative sigma mass?
So when we do the analysis, we do put a prior on the sum of the neutrino masses for 0, right? So we're not varying negative masses. The thing is just, if you then look at your likelihood and do a Gaussian fit to that, the Gaussian fit happened to peak in a non-physical region, so slightly off in the negative masses.
Does that mean there's some inconsistency though in the data?
It is a bit odd, but in the same time, I mean, it's slightly off. So the thing is, if we actually, with Desier Euclid, end up with something that looks like that, but a much smaller, doing something like that, then I think would be the time to worry. At this point, it is just, I guess what you're seeing is that the data wants more suppression due to the neutrinos with the data.
I mean, wouldn't you want the peak to be to the right of 0?
Yes, yeah. You would want the peak to be in the physical region.
I mean, not just to be 0, but to be bigger than 0, to be bigger than 60.
So that kind of depends on what you're doing with your priors, right? So you could say you add in those information from the particle oscillation experiments, and then you set your prior to be a minimum of 60. But I mean, the 60 really is coming from other experiments. There's nothing, it's not really the physical prior in that sense, right? So I think what you still would want to do is vary between 0 and up to get your constraints. But we do have a bit of a discussion on the effect that the different priors have on our constraints.
Okay, thank you.
Tessa, I think you had a question.
Yeah, hi Eva, and this is kind of related a bit to what was going on in the chat. So Tom asked, how good is that parameterization of the growth rate, the omega matter to the power law gamma as a parameterization of modified gravity? And Tim pointed out that it works very well for DGP, and Phil gave a link to some other models. I commented that I know it also doesn't work quite well for a number of other models. And the reason for that is that a lot of models would give scale dependent growth. So it would depend on what value of K you look at. And obviously that information is not preserved when everything is kind of compressed to this one statistic that is omega m to some power. So some of us here have wondered a bit about how hard or easy it is to do a scale dependent analysis. So get some bound on F, even something like what you did, but in different scale bins. So do you have a sense if that's, there's some calibration in the pipeline that makes that impossible, or it's just that the constraints would be really weak? Or
so the problem is when you were to do F sigma 8 in bins, that there were some of the bins are really hard to fit because they would be very just degenerate with the bias, right? So if you have your nice BAO bump in like one of the K bins, then that would be great. But kind of all the other bins would be super, super unconstrained. So even if you just have like 3-4 bins, they would be very, very loosely constrained, at least with our current data. I think Hector said that at some point he tried it and the results were just really, really bad. But the alternative also would be not to do the compression at all, but just to have your full likelihood, have your power spectrum as your full likelihood, and then combine this where you have like a Boltzmann code with a certain modified gravity theory that then gives you the K dependency, and then you fit it directly. That kind of has the downside that analysis is very, very slow and fairly complicated, because then you have your convolution with the window function, you have your complicated RSD model that is kind of, when you have the F sigma 8, it's like a nice simple thing. There are codes out there and papers out there where they do look at the full power spectrum. The question then partially is, so this F sigma 8 analysis is really, you could say, the more conservative approach, because you're a bit agnostic when you're doing that, right? You're just saying is, okay, we fit the amplitude, we don't assume much else. Sure. The question really is, if you do this full power spectrum analysis, how much do you trust the TNS or EFT models? Right. Is there weird degeneracies between some of the nuisance parameters and the cosmological parameters? There seems to be something odd going on with this EFT models, and when it comes to NS, so even without modified gravity, right? So I think we need to we need to figure out first how to really do this properly and robustly before we would go to the modified gravity. But it is definitely something that is a lot in discussion within DESI, and there's definitely a push towards doing any kind of modified gravity analysis with like the full power spectrum and not this compressed parameters.
Right. Okay. And the same thing's happening in Euclid as well. Yeah. Okay. Thanks for that. That clears it up a lot. Thanks.
Does anyone else have any questions? Okay, then I suggest we thank Ava again for a very nice talk and some very interesting discussion with the questions. I certainly learned a lot. So on behalf of everyone, thank you very much.
Well, thanks for having me.
Thank you very much.
Great, thank you.
We'll stay online for a little bit, just for informal sort of chat and discussion. So if you'd like to stay on and chat with Ava, then please do so. Otherwise, thank you very much for attending.
Eva.
Yes.
I wanted to ask you about this NS thing with EFT, because I hadn't noticed this, but I guess I have